Hello, everyone.
Hello.
While we're waiting for people to come in, does anybody have any questions about anything? Now would be a super time to ask. I don't know what that accent was, so just made it up on the fly.
I have a question, but it's about my lab. So can I talk to you about it after class?
No problem. Who's this? This is Tristan.
It's me, Tristan.
Gotcha. No problem. Another one coming in now. Anybody else? Otherwise, I guess we'll just get started. So we're starting chapter 6 now. If I remember correctly, we had not started with chapter 6 in this class. I'm going to double check that right now just to make sure, because I can. That helps. So this was D01C, D01C, and that should have been. I didn't write it. I think I wrote it wrong. Yeah, the last thing I did was basically inclined planes and that sort of stuff. I might have marked it wrong as D01B because I don't see a D01C here, and I do often make that mistake when I go to type the name of the actual file that I've put onto Google Docs. Has anybody actually downloaded the Google Docs file for last time? Anybody? Okay. I will check and see if in fact, I remember going back and correcting one. Maybe it was a D01C that I corrected and I just left it in my phone as D01B. But either way, we're going into chapter 6, and chapter 6 is about Newton's law.
Oh, were you talking about the lecture notes, sir?
Yes.
Oh, okay.
Yeah. I put them up immediately after class, unless I got a class right after class, in which case I do it after that class. And even if I have lab next, I usually do it within 30 minutes right after I introduce the lab. So y'all can check your Google Docs for that. All right, so chapter 6 is about Newton's law of gravity and Kepler's law. So I normally start off by giving you Newton's laws of gravity, telling you how he came up with it, and then listing Kepler's laws. And then I solve some simple problems with it. We don't do terribly much with this yet. We can do more with Newton's law of gravity once we study angular momentum. So we'll revisit it then. But let me tell you the story. So according to to Newton Sprinkipia, I've got like several versions. Here's one of them. So you can see it's a pretty big book. And this is an English translation, probably the best English translation. But you can see that's a lot of stuff. And the reason why it's so long is he didn't have, access to computers and calculators like we did. So a lot of the stuff he did, rather than take the time to do long, tedious calculations of tangent and sine and cosine, he did everything geometrically. So there's tons of geometric drawings and stuff. And then he made really precise geometric arguments to reach very exact and correct conclusions, which is amazing. But it's really hard to read other than the sentences. The sentences are straightforward, but when you get to the geometry, unless you really know your geometry well, it can be quite a bear. But what he said was he was sitting under an apple tree in his mother's orchard when he realized that the moon and the apple were very much the same. And what he meant by that is eventually the apple will get so packed full with water and moisture, and the stem will start to dry out such that it'll get so heavy that the stem can't hold it anymore, and the apple will fall to the ground at 9.8 meters per second every second. What he realized is that if the Earth is here and the moon is going around it, in order for the moon to go instead of straight up from that spot there, it has to have some centripetal acceleration pulling it in. And he, of course, had already derived that expression as we did in class, v squared over r. And what he said is, I wonder if that's the same acceleration that the moon is feeling. Of course, the moon is a lot farther away than the apple. The apple, in fact, and this was another part of his brilliance, he said the apple was about 1 Earth radius away from the Earth. And in other words, he knew to measure it from the center of the Earth. And then he said, well, the moon is actually 60 Earth radii away from the center of the Earth. So he said, what if this gravitational thing, this thing that's pulling the Earth, falls as 1/r². He had been studying light, and he knew that's how light behaves. So why not consider that for gravity? Later, it turns out we actually know that it does that for not only gravity, but it also does that for magnetism and for electricity and light. Like I said, stuff like that. It's in fact has a very deep meaning. So deep that when Einstein became famous, they asked him about ESP, telekinesis, extrasensory perception and stuff like that. He said, if you show me it obeys a 1/r² law, then I'll believe it. That's never been shown, by the way. So there's no reason to believe that actually works. But anyways, we'll go on from that. So let me show you what he actually did. So I'm going to turn on my document cam. And what Newton did was Newton said, okay, well, we have Earth that essentially is sitting still. It's really not. Okay. It's sitting still. In fact, it's actually orbiting about the center of mass of the two, which is about 7/8 of the way out from the center of the Earth to the edge. So if this was actually the Earth, say, maybe right about here is where the center of the Earth-Moon system is. And that's the point that actually follows the elliptical path that we'll talk about in a second. Now, we're going to ignore that for a second and just assume the Earth revolves around its own center. So that's the Earth. And then we'll have the moon way out here. And the moon at this point is going that way with some velocity v. We know that this distance from center to center is 60 times the radius of the Earth. That's the symbol we use for Earth. And we know that this distance right here from the center to the edge is the radius of the Earth. Okay. So what he also realized is that the time required for the moon to make one trip around here was known. It's about a month, right? So I'm looking up my notes real quick just to make sure I use the right numbers. Yeah, that looks pretty good. That's not the ones I wanted though. Hold on a second. Yeah, this will work. Okay, so he knew that, right? And he also knew that the velocity, if we assume a circular orbit, which it's pretty close. In fact, what I'll tell you is that if you took our orbit and drew it exactly the same scale as a circle and put the circle next to it, without a good deal of measuring, you'd have a hard time deciding which one was the circle and which one was the ellipse. So when Kepler discovered that they were ellipses, it was a pretty impressive thing. But we know this velocity should be 2 pi times 60 Earth radii, because that's the orbital radius, over the period of the moon. Well, we know the period of the moon is 27.3 days. Okay. So the velocity of the moon should be 2 times pi times 60. And then we just take the radius of the Earth, and the radius of the Earth is 6.38. A good rule of thumb for this, by the way, is 6 times 10 to the 6 is the radius of the Earth. But it's 6 times 10 to the 6 meters. And then we divide that by 27.3 days times 1 day is equal to 24 hours. And then 1 hour is equal to 3,600 seconds. So now we've got it all in meters per second and stuff like that. So we can get the velocity. In fact, when I calculate that velocity, it turns out to be 1.02 times 10 to the third meters per second. Okay, it's 1.019 actually, but I figured the 1.2 is good enough. Okay, so that's how fast it's going. It's literally going 1,000 meters per second. That's pretty darn fast, right? Well, the acceleration of the moon should be equal to v squared over r. Okay. So we can now, having that v and having the r being 60 Earth radii, we can calculate that. But Newton was smarter than that. He just started from the very beginning and said, wait a second, If the acceleration is proportional to 1 over r squared, then what that means is the acceleration for r equal to 1 Earth radii should be 9.80 meters per second, but the acceleration at 60 Earth radii, that should be 9.80 meters per second divided by 3,600, because 1 over r squared, if I take 60 times r, then that's going to be 60 times r squared. So I should actually divide that 9.8 by 3,600. And when he did that, he got 2.72 meters per second. So there's his hypothesis. His hypothesis is that the force of gravity, whatever that may be, however that may work, should cause the acceleration of the moon to be 9.80 divided by 3,600 if the force is in fact inversely proportional to the square of the distance. So that was his hypothesis. Now he goes and calculates what's the actual acceleration of the Earth. Well, we'll say 1.01, or excuse me, of the moon, 19 times 10 to the third meters per second. I'm going to square that, and then I'm going to divide that by 60 times 6.38 times 10 to the sixth meters. And when I do that, I get 2.72 meters per second. At that instant, Newton was the only person on planet Earth that knew exactly why the planets orbit the sun, why the moon orbits the Earth, why the Medicean moons, which we now call the Galilean moons, orbit Jupiter, so on and so forth. It was because a heretofore unknown force called the gravitational force, and he said that that gravitational force must be equal to some constant, I'll put it equals instead of a proportional, equal to some constant g, the gravitational constant of the universe. It must be proportional to the product of the masses. In other words, any two things that have mass are going to have a force of attraction between them. And that would be written as m1 times m2, and inversely proportional to the square of the distance between them. So if, for instance, you took two objects that had a certain force on them and you double one of its mass, that force would become twice as big. If you tripled the other mass instead, the force would become 3 times as big. But if you doubled the mass and then tripled the other mass, then it would become 2 times 3 or 6 times as big. Also, if you cut the distance in half, notice that's r going down and that's in the bottom, so F must go up. You would actually increase the force by a factor of not 2, but 4, because 2 squared is 4. So cutting the distance in half increases the force by a factor of 4. And he also said that it acts as a attractive force connecting the center of mass of M1 and the center of mass of M2. The gravitational constant was determined to be 6.67 times 10 to the negative 11th. The units are Newton's meter squared per kilogram squared. So that's it. That's Newton's law of gravity. And in fact, it's accurate enough for us to get to the moon. We could get to Mars. We can actually, as far as just the orbital mechanics so that we can get to the planets in our solar system, Newton's law of gravity works just fine for that. The problems come in where you have to use relativity in dealing with the time and stuff like that. So if you wanted to be very precise about your time and wanted it to say 4 or 5 decimal places, you'd have to correct for special relativity and general relativity for that. But other than that, it's pretty good. So remember, it acts along a line connecting the two centers of mass of M1 and M2, and it's inversely proportional to the distance between those two centers of mass. We'll write that out in vector form later. I will tell you also, remember I said this is a ubiquitous type of force. It turns out the Coulomb force, which is the one for electric forces, and it says like charges repel and unlike charges attract. That's actually K, and then instead of mass, it uses charge, and we use a symbol Q for that, Q1, Q2 over R squared. That's exactly the same form. Now, here's the big difference. K is equal to 8.99 times 10 to the 9th, not negative 9th, 10 to the 9th, Newtons meters squared per Coulomb squared. So you can see the forces are exactly similar. And in fact, what I recommend you do as an extra credit is and I believe the extra credit turn-in spot is on the last week's already. So it's already posted on last week's for you to turn it in. But basically what you're going to do is consider a proton and an electron in Bohr's orbit, okay? And I want you to calculate F Coulomb over F gravity for the proton and the electron. Now I'll give you some information to help you do that, but I think you're going to find it to be on the order of like 10 to the 44th or something. So that shows you, even though when you compare these two, it looks like the Coulomb force should be 10 to the 20th power times stronger, but in reality it's even worse, as you can see here. So you should get around that, but I want you to do this as an extra credit problem. And what you'll need, of course, is the mass of the electron, which is 9.109 times 10.
Professor, you're writing off camera.
Thank you. 9.109 times 10 to the negative 31st kilograms. The mass of the proton, which is 1.67 times 10 to the negative 27th kilograms. Let me double check that figure. I'm doing these out of my head, so there's always a chance for me to screw up. 1.67 times, yeah, that's right. Okay. You've got the constants. You also need the charge, and you're going to ignore the signs, by the way. I'll say ignore the signs when doing calculating. Just do both positive. Okay. But the charge of the electron is negative E, which is negative 1.602 times 10 to the negative 19th coulombs. And the charge of the proton is just E, which is equal to 1.602 times 10 to the negative 19th coulombs. So you've got that, you've got that, you've got that, you've got that. And in fact, you may or may not realize whether you need this, but 5.42 times 10 to the negative 11th meters is the Bohr radius. So that's how far apart they are. Okay, so that's what you'll need to calculate. Any questions on that? It's like
no, can you just hold the screen there?
Yeah. So I did this on Friday with my morning Friday class, and then I went ahead and copied that module for turning it in into the other two classes. So you'll actually find that module in the other two classes, or in the module for last week, if I'm not mistaken. If you don't see it there, let me know, but that should be where you turn it in. When I said ignore signs, meaning I just want you to put positives in for Q1 and Q2. All right, so let's do some stuff with this now. Let's do some actual calculations with Newton's law of gravity. Well, actually, no, let's go ahead and do Kepler's laws first. I'm going to say Kepler's laws. Now your book has them written, so you can copy them out of there if you want, but I'm just going to go over them and explain what they are. So prior to the Copernican revolution, Aristotle had more or less created all the laws of physics as we know them. And of course, it wasn't even called physics. It wasn't even called physics during Newton's time, in fact. But the fundamental idea was there was, 4 elements if you don't count Milo Jovovich. But basically there's earth, wind, fire, and water, and they had their natural places to be. And if they were moved out of that natural place, then they would naturally move to try to get back to that place. Any other kind of motion, though, was what we call violent motion, and that required some kind of sustaining force, if you will, to keep it moving. So if you burn a log is part earth, but it's also part fire, and fire being what the sun's made of, its natural place is slightly above the air. The air inside of it has a natural place that's wind, of course, and that's above the earth. But then the earth part is trying to go to the actual ground. So when you burn a log, you get little ashes that float up, but float up a little less, a little slower than you might expect, and that's because part of them is still earth. Okay, so that was natural motion for it. All the other kind of motions were forced, and in fact, the heavens, which is the fifth element, the quintessence, that was actually considered to be perfection. And of course, naturally, if the heavens are perfect, then the only perfect shape is the sphere. So everything in the heavens must be spherical. They could never change, because if they change, they have to change from incorrect to the proper thing, or from the proper thing to the incorrect thing. And the heavens can never be incorrect. So no change is possible. Little weird things like that where there's laws. And basically, the planets would orbit the Earth. The moon as closest to the Earth, then Mercury, then Venus, orbiting it on a crystalline sphere. But it was embedded in this crystalline sphere, and of course traced out a path that was a circle, because a circle is a natural slice of a sphere. And Mercury would be just outside the moon, and then Venus, and then outside of that was the sun, and then outside of that was Mars and Jupiter and Saturn. Okay, and that was their picture. Well, Kepler comes along after the Copernican revolution and says, okay, well, this is really what it is. I can't fit the data that Brahe has given me with anything that Copernicus has given us. So he had to rewrite everything. And his first law basically said that the planets follow elliptical orbits with the sun at one focus. So, you can take and stick a nail on a piece of a piece of plywood, and then tie a rope to it and tie the other end to a pencil. And as long as you keep that pencil perfectly vertical and that rope perfectly taut, it'll trace out a circle. Well, an ellipse is sort of like that, except you use two nails, and you use a string that's slightly longer than the distance between the two nails. And then when you keep that taut, the shape is going to stretch out to be roughly this. Obviously, that's not a very good ellipse, but that's an ellipse, okay? And these two nails are the focal points. Which the plural is foci. Okay? Now, what he said was like, one of these will be the sun, and the other one's nothing. Nothing special about the other one, okay? So there's our sun. It turns out this right here is the major axis. And that is an object, but it's also a distance. That's the distance across it, okay? And this right here is the minor axis, which again is also an object, the line crossing the orbit, but it's also a distance, okay? And in fact, half of the major axis is called A, the semi-major axis. And in that case, you cannot, when you use A for it, that can mean the actual distance. It is in some sense the average distance between the planet and the sun, because notice if the planet is right here, it's what we call perihelion. It's closest to the sun. So its orbital distance is just that distance right there. Now, if it's over here, on the other hand, if it's at the other end of the orbit.
Professor, can you hold it up to the screen real quick? Thank you. Thank you.
If the planet's over here, that's called aphelion. And you see that distance is from the sun all the way to here. Okay. So if you average those two distances, you'd say this distance plus this distance, and you divide it by 2, wouldn't you? You see that when you add the two, you get the major axis, and therefore you divide that by 2, you get A, the semi-major axis. So that's what I mean when I say the semi-major axis is in some sense the average distance between the planet and the sun. So that was his first law, that the planets revolve around the sun, and revolve is different than rotate, by the way. They revolve around the sun in elliptical orbits with the sun at one foci. And as I was telling you, they're very far from being really nice ellipses. They look way more like a circle. Like I said, if you put the Earth's orbit next to a circle about the same size, you couldn't just look at it and instantly tell which one's the circle and which one's the ellipse. They're that close. Okay. There's a lot more geometry in the semi-major axis, minor axis, things called eccentricity, stuff like that. But I'm just giving you the bare minimum of what you need. That was his first law. His second law was actually kind of neat too. And his second law basically said, okay, well, unlike what Aristotle taught us, which was that the heavens are immutable, they can't change, right? Kepler said, nope, they do. Kepler said, in fact, they sweep out equal areas in equal times. So what do we mean by that? Well, there's the sun, say. So let me do a little red circle around that so everybody knows that's the sun. And what it means is if you happen to go from this point in the orbit on day 1 to this point in the orbit on day 30, okay, you find another area. Notice we're making, if you think of this as like an elliptical shaped pizza, if you consider the planet being here, that long slice of pizza is going to not need to be as wide as this one if you're trying to get the same amount of cheese on it. So if I wanted to put the same area that's here inside of this slice, then maybe I'd actually just do, say, this far. Okay, so that would be day 1 and that would be day 30. What it means is, if this is true, if it went from day 1 to day 30 in this distance, and it went from day 1 to day 30 this distance, then when it's closer to the planet, it goes a lot faster than when it's far from the planet. He said it sweeps out equal areas in equal time. And that turns out to be exactly right. And it actually turns out to be a result of conservation of angular momentum. This just turns out to be a result of the mechanics of a 1/r² force. And then finally, his third law, basically for his third law, he took the period versus the semi-major axis for the planets, and he'd keep plotting them the various powers, and he'd get, lines like this, or lines like this, or lines like this, stuff like that, until he did t² and a³. Then he got them all lying along a straight line. And he concluded from that the square of the period is proportional to the cube of the semi-major axis. Remember Times Square, if you have a hard time remembering which one's that. Times Square is where we celebrate New Year's Eve in New York. So Times Square reminds you to use Times Squared, and then the semi-major axis will be cubed. Okay, so that's his 3 laws, and this turns out to be true as well, and it's true for all planets. In fact, you find that the time required to go one orbit, say from here all the way around to here, that time squared is directly proportional to this distance cubed, no matter what the body's orbiting, what body it is. So it works for Galilean moons orbiting Jupiter. It works for the moon orbiting the Earth. It works for satellites orbiting our Earth. It works for satellites orbiting Venus, anything like that. It's pretty amazing. Now, Newton comes along, having invented or discovered a formula for gravity. Newton first off shows that there's only 2 types of forces that can make stable orbits. This is Newton now. And that's F equals kx, which is called Hooke's law. And F is proportional to 1/r², which is his gravitational law. And in fact, when one of those 2 forces is acting, there's only a handful of orbits that can actually happen. And what he found was the orbits are conic sections. So here's a little imagination game. So you've probably been to, I don't know, a car repair shop or a junkyard or a gas station or something that has those cups that are shaped like little cones. Well, imagine two of those touching tail to tail like this. And in fact, they go on for infinity both directions. So this goes to infinity and this goes to infinity. Okay. All the ways you can slice that make the conic sections. So for instance, if I slice it sort of parallel to this side, but on this side, I will get a shape that goes and gets wider and wider forever. That's called a parabola. Okay. If I, on the other hand, slice it parallel to the axis, then I get something that looks like this. But because it's parallel to the axis, it also has a part up here. And that's called a hyperbola. If I slice it perpendicular to the axis, it's going to look like an ellipse here, but it's going to be an actual circle. And if I slice it at some angle larger than this, then I will get an ellipse. And that's what Newton showed. Newton showed that there's only two forces that make stable orbits. F equals kx, called Hooke's law, and F equals is proportional to 1 over r squared. And that those produce orbits that are either circular, elliptical, hyperbolic, or parabolic.
You did that through doing the calculations and then drew a cone just to explain it.
Well, actually, the cones already existed. Everybody had already been studying those already, but he was able to show mathematically that the only orbits you get is basically a sum of squares, or in some rare cases where you get basically the y is proportional to an x squared or the x is proportional to a y squared, which would be the parabola.
Okay.
So, yeah. So that, yeah, that part of the math had been worked out before, but yeah, he just grabbed it and said, well, this is obviously the case. So yeah, it was a pretty freaking brilliant move on his behalf. He also did something equivalent to conservation of angular momentum and showed that this had to be true. And that's angular momentum conservation. And he was also able to show that this had to be true. And that turns out, again, not necessarily the way he did it, but in our ways of looking at it, this is conservation of energy. Okay. So it turns out you can actually do energy methods for the orbital, and you will get an equation that gives you this, or you can actually do it from basic. Newton's second law says G, mass of the Earth, mass of the sun, over A squared. If we assume A is a radius and it's just a circle, then it's just going to be A. In fact, when you do this with an actual ellipse, the same comes out. There's just a little correction to it. But if you say that's equal to m of the Earth times v squared over r, which is again A, sorry, then guess what? You can automatically see this A is going to cancel out with that one. That radius, in other words, is going to cancel out with that one. And when you say v is equal to 2 pi a over t, you're going to get, oh, by the way, you can also say that this m is going to cancel out with this m. You will get G m sun over a is equal to 4 pi squared a squared over t squared. And I think you can already see that that becomes t squared is equal to 4 pi squared over g mass of the sun times a cubed. And you can see basically that's it. That's Kepler's third law. Now it makes sense though. It's got a constant in there that tells you something. For instance, if you did it more general and took into account the fact that the orbits can be ellipses, basically the only difference would be this g would be multiplied by parenthesis mass of the sun plus the mass of the planet. So, but you can see that is exactly what Kepler found, and Newton basically said, yeah, of course Kepler was right on that, even though Kepler had done it all from data as opposed to any underlying theory about why it did so. He just gave you the results so that we could make, tables of where the planets would be at certain times of the year, because remember, they were making calendars, and governments were working on calendars with the idea that astrology was a real science. So they had to know things like where the planets would be in a given constellation, to make good decisions, and also to celebrate certain holidays and stuff like that. So that's Kepler's three laws. The first one says the planets sweep out or follow elliptical orbits with the sun at one focal point. The second one says they sweep out equal areas in equal time, which means they speed up when they're closer to the sun and they slow down when they're further from the sun. And the third one says the square of the period is proportional to the cube of the semi-major axis. I should mention, though this is not what this was meant for, it's completely consistent with it. So if you ever wonder which one's faster, say Mercury or Venus, y'all know that Mercury orbits is the closest to the sun. So therefore its speed is actually going to be faster than Venus's speed as well. So even though it's not meant to cover two separate orbits, I'm just telling you it's completely consistent with that. And I use that as a memory tool when I'm trying to remember which planet would be fastest. The one that's closest to the sun has to go fastest in order to keep the sun from pulling it in. Okay, any questions on that? All right, so that's sort of the intro to Newton's law of gravity. What I want to do now is I want to actually do some stuff with Newton's law of gravity to, for instance, show you how powerful it is. And the first thing I'll do is remind you that the weight that we've been using in class, weight equals mg, well, that's actually gravity that's causing that weight. So because of that, you might want to think, well, wait a second, if weight is the pull of gravity, then that means m times g, my mass times gravitational acceleration, must be equal to g times my mass times the mass of the Earth over approximately the radius of the Earth squared. And you'd actually be right. In fact, you can see right now that the mass myself cancels out, and then I'd get g is in fact equal to g times the mass of the Earth over the radius of the Earth squared, which is 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared, times the mass of the Earth, which is 5.28 times 10 to the 6. Let me double check on this real quick though. Let's do this one. Sorry. 5.98 times 10 to the 24th kilograms. And then of course we know the radius is 6.38 times 10 to the 6 meters, and that's going to be squared. When we put that in our calculator, I do 6.67 e to the negative 11 times 5.98 e to the 24th divided by, now your calculator is smart enough to know that the square only goes to the thing immediately to its left, so I don't have to put parentheses around it. And lo and behold, I get 9.799088, which obviously is way more sig figs than is represented here. So really, if I use 3 sig figs, that should be 9.80 meters per second every second. And you can see that that cancels out that way. Basically, A kilogram here is going to cancel out with that. The meters are going to cancel out with that. So I got a Newton per kilogram. But remember, a Newton is from F equals ma. 1 Newton is 1 kilogram meter per second squared. So if I take a Newton and divide it by a kilogram, I just get a meter per second squared. So that checks. Okay. So that's one thing we got. We know that, wow, gravitational acceleration is actually made up of constants that we know. That's cool. So that will be example 1. What you might also want to know is, I wonder how much gravity is affected by going to great heights on the Earth and to great depths on the Earth. So let's do that with example 2. Okay, so what I'm thinking of here with example 2 is I'm going to calculate the gravitational acceleration at the highest point on Earth, and then I'm going to calculate the gravitational acceleration at the lowest point on Earth. The highest point on Earth, does anybody know what that is?
Mount Everest.
Yeah, Mount Everest, exactly. And that's, in fact, if you read the book Into Thin Air, you know that that was supposed to be 29,025 feet was the height of Mount Everest. But since that time, we've actually had a major earthquake, and now the distance is 29,032 feet, if I remember correctly. And I'm actually going to pull that up real quick. 29,032, yes. So it went from 29,025 to 29,032 feet, which obviously we're going to convert to meters. So let's do G for Mount Everest. Well, that's going to be 6.67. I've already worked out the units, so I'm going to leave them off this time. Times 10 to the negative 11th times the mass of the Earth, which is 5.98 times 10 to the 24th. And then I'm going to divide it by not the radius of the Earth, but the radius of the Earth plus the height of Mount Everest. So that's, notice 6.38 times 10 to the 6, that's really 6,380,000 meters. And the 29,032 feet, that's going to become, in fact, 8,848.95. And that part's going to be squared. Now notice this just comes up to basically this digit right here. It's where that 8 is lying.
What's that value that you added?
8,848.95 meters. That's this converted to meters. Which really, that's an extra sig fig for us there. So when I do this calculation, lo and behold, it turns out that I get 9.7720 meters per second every second. And these are extra sig figs. So I basically changed by the delta G over G is actually 0.03 over 9.80 times 100 for percent. That gives me about 0.3% difference. Okay. So at the top of Mount Everest, the gravitational acceleration got small. At the bottom, the deepest part of the ocean, anybody know the name of that one?
Mariana Trench.
Yeah, it's the Marianas Trench. And that's 36,161 feet deep, which is going to be 11,021.9 meters. Okay, so if I want to calculate the G at the Marianas Trench, then that's going to be 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th over 6,380,000 minus 11,000 or excuse me, not 11, yeah, 11,0219, 021.9. And this one's actually got 5 sig figs as well, so that digit's extra. Now I got to square that, and lo and behold, that one's going to be 9.8330 meters per second, which I think you can tell is again about 0.3% different. So when we're dealing with even the height of Mount Everest and the depth of the Marianas Trench, we really don't deviate from G being more than about 0.3 off, 0.3% off. So that's literally 3 out of 1,000. So yeah, there's no need to worry too much about correcting for G at various elevations. It's not huge. It's big enough for us to detect. We can use that as a altimeter if we wanted to. For instance, we can actually use it more easily to detect deposits of higher density material directly below us, because it turns out the Earth is not just a smooth, all isotropic material. So, any questions on that one?
There's actually in surveying, like you don't measure elevation relative to sea level anymore, just because we recognize sea level isn't level.
Right.
But one of the ways that you do is actually measure relative to the geoid, which is a model of wherever gravity equals 1g.
Gotcha.
And you can actually, if you're leveling, trying to figure out a level difference from one side of the mountain to the other side of the mountain, using traditional levels, go over the mountain, you'll end up at a different level than if you go around the mountain, just because
Wow.
gravity of the mountain.
That's cool. Yeah, I worked with a geoid before. I used to do some topo maps and stuff like that. I did surveying work when I first started as an engineer. I just went to an engineering firm and I told them I was interested in doing engineering. I was a physicist. The woman that hired me was the owner's wife, and she didn't necessarily know anything about physics or what I was capable of. But she said, well, we certainly need somebody in surveying. I said, well, I've always wanted to learn surveying. So she hires me at that. And then like I'm out there for 2 weeks, and then the lead engineer looks at my resume and calls me in and says, what are you doing out in the field? I said, well, I like it. It's kind of cool. He said, yeah, we can make more use of you there. And that's when I started doing wastewater treatment. He gave me Metcalf and Eddy, and it's this big Bible of wastewater treatment, and said, read over that and give me a report. So that's how my career started. But yeah, I love surveying, man. It was awesome. But yeah, they do a lot of cool stuff with that. You can use magnetism, and actually, in fact, they used, when I did it, are you surveying? You took that in a class, right? You didn't do it for a living?
I'm doing right now, I'm working for a bathymetric surveying company. So it's like surveying above land, except for it's all underwater.
Gotcha. Yeah. So it was funny. I own this calculator, and I've owned it since I was in grad school. And sure enough, I took my the theodolite that we use and the surveying instrument you use, and I pulled the computer open that we're typing into and realized they're using the exact same computer in my surveying equipment. So it's literally like one little chip they added for a surveying insert, and that was all being done with my old HP calculator. So yeah, it was pretty cool. I love doing drafting. You take the data points in and rotate them onto a plat, and it's just fun stuff. But yeah, there's a lot of cool mathematics and stuff that can come from the physics of actual life when you're trying to solve problems. So, do you guys think the picture's any better today? As I said, I told you I bought a 50-foot coaxial or Ethernet cable in hopes that it would give a better production. It's going to be at least prettier when we record it. So, all right. Any questions? Anybody? Sorry about that. Got on a tangent talking about.
To follow up on your video quality thing, I don't think it's that much better. It is a little bit better, but that's a big cable, 50 feet.
Yeah. It's pretty much a 10-foot or 50-foot. They sold it by a foot, but the guy that was there at Home Depot didn't know how to put the ends on, and I was like, okay, well, I'll just buy this.
What cat is it?
6.
Okay.
Yeah, I think 6 is about the best you can get normal people, but I know it goes up to like 8 and 8A or something now. But
yeah, Cat 7 is also pretty good for pushing over distance too, but yeah, be good.
It looks a little better on my side, but I don't even know how that would be possible. All right, so going into the next part, we've got 25 minutes left. There's some other types of problems I want to work for you. One is you got to recognize that the vector force, or that the force of gravity, like all forces, are in fact vectors. So we need to know how to deal with such forces. And I'm going to do one just, technical method, easy peasy or whatever. But let's imagine for a second, I'm going to put this one in a coordinate. I didn't do that with the previous classes, but I'm going to do it with this one. So what I'm going to do is I'm going to imagine an XYZ coordinate system. And actually, all I really need is X and Y, because I want to put them all in the plane. So I'll put an XY here. I know y'all aren't seeing that yet. It's a little high. Oh, a second. So my stuff, well, I got ceiling fan in here. It's wreaking havoc. So I'm going to put one mass right here at the origin. So that's 0, 0. I'm going to put another mass right here at 100 meters. I'm going to assume 3 sig figs with everything, of course. And then dead center over the top, I'm going to put another mass up here. And that coordinate is obviously in the X is going to be 50.0 meters. Now I got to figure out what the Y is, but what I'm doing is I'm making it a right triangle. Excuse me, a equilateral triangle. So this is 60 degrees, and this is 60 degrees, and that other one's of course 60 degrees. So but really what I need is I needed to make sure I have the right height. And obviously, if this is 100 meters and this is 100 meters, we have basically 100 meters right here with a 30 degree right there. And I need this height. So I can see that cosine 30 degrees is equal to the height over 100. So I need 100 times the cosine of 30. Again, looking at my special right triangle, that's a 30 being next to the square root of 3, and the 60 being opposite that. This is the 1 here, and this is the 2 here. So we can see that the cosine of 30 is root 3 over 2, or 0.866. So I'm going to say this is 86.6 meters up. Okay. This one's going to be called mass 1. And its mass is going to be 0.16 times 10, and let's say 16. I'll just leave it 2 sig figs on that one. 16 times 10 to the 9th kilograms. This one, M2, is going to be 0.16 times 10 to the 9th kilograms. And this one's going to be M3, which I'm going to say is 1 times 10 to the 3rd. 1.0 times 10 to the 3rd kilograms. Okay. What I want to find out here is what is F3? In other words, what's the total force on this one mass at the top as a result of these two? From a formula standpoint, we know that F3, that's what I'm calling it, is the force on 3 due to 1 plus the force on 3 due to 2 in vector language. Okay, so there's a couple different ways you can make these into vectors, but normally what we do is we go ahead and use Newton's law, and we do the same thing with Coulomb's law, ignoring the signs because you don't have signs in Newton's laws, but in Coulomb's law you have plus or minus. You just treat everything as plus, and we use that just to calculate the magnitude. So let's, for instance, calculate the magnitude of F31. Well, F31 is equal to 6.67 times 10 to the negative 11 times 0.16 times 10 to the 9 times 1 times 10 to the 3 over 100 squared. Now, the whole reason I did that 0.16 is I knew it would cancel out the 6.67 roughly. So in fact, that result comes out to 1.07, which is 1 extra sig fig, of course, 1.07 times 10 to the negative 3rd newtons. Okay. Now that's the magnitude, and there's 2 ways I could make a vector out of that. Or 2, there's a ton of ways, but one of the ways I'm thinking of is I could make a unit vector that points the direction that this force points, and then I just multiply that by the unit vector, and I'd be right on the money. Okay. Well, I know that this vector is the vector that represents the force acting on mass 3 as a result of mass 1. I know that's an attractive force because that's the only kind of force gravity is. So I know it's actually along this line. So if I can find some way to represent that line by a vector, then I can easily do it. Well, what I have to do is I can take 0, 0, because that's the final point. I can take 0, 0 and subtract from it the initial point, which is 50.0 meters, 86.6 meters. And that would give me an actual distance vector by doing this. I could say 0 minus 50, that's negative 50.0 meters I hat. And 0 minus 86.6 gives me negative 86.6 meters j hat. And that vector is literally the vector that points from here to here. It's that long and everything. Okay. So that means it should be 100 meters long. Let's check that. The magnitude of D would be the square root of 50.0 squared plus 86.6 squared. So if I do that, I'll say 50 squared plus 86.6 squared. And now I'll take the square root of that. And I get 99.9978. Well, I'm only using like 3 sig figs, so that's definitely 100 meters in length. So that gives me a vector, but its length is 100 and it's got a unit of a meter. So if I multiplied this by that, the units would be in Newton meters and the length would be 100 times too big. It'd be 1.07 times 10 to the negative 1. But if I make a unit vector out of it, I can call it d hat. And that's just by taking the vector d and dividing it by the magnitude of d. That's a unit vector. So all I'm going to do here is I'm going to take the 50 and divide it by 100. So it's negative 50.0 meters over 100 meters I hat. Notice the meters are canceling out. Minus 86.6 meters over 100 meters j hat. So this gives me 0.5 negative I hat. And this gives me, of course, 0.866 j hat. No units. Okay. So in fact, my F31 is equal to just the magnitude of F31 times d hat. You could even call that if I wanted to. Whenever you put a hat on something, that means a unit vector. So when I multiply these two, I'm going to say 1.07 times 10 to the 1.07 e to the negative 3 times 0.5, negative 0.5 technically, gives me negative 0.000535 newtons I hat and 0.00107 again times negative 0.866. And I really am only keeping 3 sig figs, so that's far enough. This one gives me negative 0.000927 newtons j hat. So that could be my vector. Okay, that's a way to do it. It's not necessarily the best way, but it always works. That's kind of nice. So you can always find a vector that points the way you want it to, divide it by its magnitude, and just multiply that by the magnitude of the vector. And since it's a unit vector, you're not changing its magnitude or its units, so it all works. Another way is to just say, hey, wait a second. I know that that is 1.07 times 10 to the negative 3 newtons. I know that this is 30 degrees, and I know that this is the y component. And if I call this and this, remember I said up is the positive y direction and right is the positive x direction, then this would be 1.07 times 10 to the negative third newtons times the cosine 30 degrees. And it have a negative in front of it. And this would also be negative 1.07 times 10 to the negative third newtons times the sine of 30. When I do that, guess what I get? So negative 1.07 times 10 to the negative 3. And remember that 7 is actually an extra digit. So I really should be keeping these to 2, not to 3. So let's see, 1.07 e to the negative 3 times negative, and I just did times negative because I wanted the negative to come out my calculator, times negative, now take the cosine of 30 degrees, and I get 0.00926 negative 92, actually I should round that to 7, 927 newtons in the I hat direction, or excuse me, in the J hat direction, because that's the Y component. And then with this one, I'm going to get minus 1.07 e to the negative 3 times negative sine of 30, which we know, of course, is 1/2. And I get, whoa. Oh, no wonder. 1.07. Look what I hit the E instead of the double E. 1.07 EE negative 3 times negative 1 times sine 30. And you get 0.000535. Again, that's one extra digit, just like that one is. Newtons in the I hat direction. So you got the exact same vector either way. That's the key point. So that was a little more thorough than I was able to give in my other 2 classes. So I just wanted to do that once to make sure you understood. Now that's the F31 right here. Right. And if you want to see what F32 is, well, that's the same thing, except it points this way. And notice the 2 masses are the same, 0.16 and 1 times 10 to the third. The distance is the same. And of course, the G is the same. So the magnitudes of these vectors are going to be the same. And in fact, the Y component is going to be the same as the Y component for that one. And the X component is going to be the same thing, but positive. Whereas this one was this, and then negative this way. So if I go to add these, really all that's going to happen is the X component is going to cancel out for the 2 of them, but the 2 Y components are just going to add to each other, basically making twice as big a Y component. So I now know without a doubt that F3 is just the sum of the 2 Y components. So I can now say F3, which is really F31 plus F32 is equal to, noticing that basically what's going to happen is this one's going to be negative, but F32 is going to be positive. So F32, this is going to be negative 0.000927 newtons J hat. And this one's going to be plus 0.000535 newtons I hat. When you add these 2 together, those cancel out and these 2 add together. And ultimately, I will get (1.85) times 10 to the negative 3 newtons in the negative J hat direction. That's it. So that's one of the things you have to be able to do, is take a formula that can give you a magnitude and take a description like Newton saying it acts along the line connecting the 2 masses and make a vector out of it. I just showed you how to do that. So one way you can always make a vector is you always can take the coordinates and do the final point minus the initial point and just leave the subtraction as if the x's gave you something to be multiplied by I hat and the y's gave you something to be multiplied by j hat. Okay, and then you'll get the vector, but the vector comes with the units that the numbers had. So for instance, in a coordinate system, if you were measuring the coordinates in meters like I did here, it's going to come out in meters. But as you can tell, when I computed a unit vector, it is truly a unit vector because the meters cancel out. So it's literally a unit long, meaning a unit, period, not meters, not kilograms, not feet, not anything. Ain't that kind of neat? Any questions on that before we move on?
I think we're okay, sir.
Okay. All right, I got one more thing I want to show you, and that's how to make a formal vector formula for the law of gravity. I usually don't do that in this class, but I noticed your book does. And I also noticed that when I show it to my students in the second semester, because we have to do it there with Coulomb's law, it's kind of confusing for them. So I'm thinking maybe introducing it early might help. So to do this, I'm going to draw an XYZ coordinate system. You always got to make sure your coordinate systems are right-handed. And one way you can do that is X coming out of the board or paper, Y going to the right, and then Z going up. And what I mean by right-handed is, I'm going to flip the camera real quick and let you look at my beautiful smile. So one way you can do it is you hold your right hand like this. Everybody see this like a gun or something. So the index finger is going to represent the x-axis. The middle finger, which is sort of like grabbing a trigger, if you will, that's the y-axis, and then the thumb points in the z-axis. With your right hand, if you do that, then everything works. What I've just drawn was x coming out at me, y going to the right, and then z going up. So from my perspective, I've got exactly right what I drew over there. Okay. Another way is you can think of the cross products. If you cross a vector in the x direction with a vector in the b direction, the product of that, the cross product of that should point in the z direction. So that's another way of thinking about it. If you don't do a right-handed coordinate system and then you start doing calculations based on it, you will get the answer wrong unless you're just lucky. And the next time you do it, you probably won't be so lucky. So it's too much work to work out the details if you did a left-handed coordinate system. So just always be careful and do that. So what I'm going to do first is I'm going to represent mass M1 over here. And I want to suggest that this means if I dropped a vertical line, it would land right here. And this is my x-axis going back behind the page, say. Now, if I draw where it hit the XY plane, if I draw a line parallel to the x-axis, that'll take me to my y coordinate. And if I draw a line parallel to the y-axis, that'll take me to my x coordinate. So this is evidently behind the paper and to the right of the origin and up, in fact, a certain distance, which you could do like this and recognize that that would have to come back here and that would be the height. Okay, so that's one vector, or that's one mass. Now I'm going to put the other mass, let's say, right here. This is going to be M2. And this one, I'm going to say, if I drop a vertical, it's going to hit right here. And then I draw parallel to the x-axis, and that gives me my y. And I draw parallel to the y-axis, and that gives me my x. And then, of course, doing this, that gives me my height. Okay, so I'm just working real hard to make sure you guys see this in 3 dimensions. I don't even know it's that important that you see it in 3 dimensions, but I can't stand it when someone can't. So I always try to do something about it. So this vector right here, from here to M1, we're going to call that vector R1. And this vector right here, we're going to call R2. Okay. Now, according to Newton's law of gravity, the force of attraction should act along a line that connects these two guys. So you should be able to imagine a line going like that. And the force of attraction should be somewhere along that line. He's in the office with me. Okay. So F12 will be the force on 1 due to 2. Due to 2. So that's my terminology. When I say F12, I mean the force on 1 due to 2. That's the key thing I'm trying to get for you to understand there, okay? Now, what I want to do is think of these two vectors, R2 that's coming out towards me and R1 that's going back into the desktop. Is there a vector operation between R1 and R2 that I could do that would give me a vector parallel to that? Either pointing from this one to that one or from that one to this one? Anyone?
Addition.
What did you say?
Vector addition, if you add like, I can't really see the subscripts, but if you add one of your vectors to the vector that you want to get, you'll get your other vector.
Okay, that's close. Remember, they're tail to tail. So if you tried to add them, you'd have to complete the parallelogram and you'd get basically the vector pointing this way. But you're close. You're on the right track. Anybody want a different try? Do y'all remember any vector that when you put the two vectors tail to tail, you connected the tips to get the new vector?
Yeah.
Yeah, that was the subtraction. So let's look at this for a second. Let's say R2 minus R1. That's defined to be R2 plus the opposite of R1. Okay. So what that would mean is you take R1's head and you put it down here. That's the opposite of R1. And then you have two vectors that are head to tail. So you know you just go from the tail to the head. And in fact, that would point from M1 to M2. That's exactly the one we want. So the vector from here to here is R2 minus R1. So that vector actually does work. And it happens to be the distance, the length of it happens to be the distance that we need from Newton's law of gravity. Now, we might choose to define this vector, since it's 2 minus 1, we might call it R21, and that would work just fine. But then your law of gravity would be F12 is equal to G M1 M2 over R12 squared times R21. But look what happens now. If I remember what I showed you about a vector, when you make a vector by subtracting or something like that, you've got the units of the vector, right? So by multiplying this magnitude by that vector, I've canceled out one of these magnitudes, so it's not the right size. So really I should take and do R12 down here as well, then that'll make that a unit vector. So you could say G M1 M2 over R12 unit vector. All of these are valid formulas. Okay. I don't like the 1 and the 2 being the opposite, but if you use that to remember, then that's great. Okay. Another thing you could do is you could make the vectors actually match subscript order, and you could say it's G M1 M2 over R. I'm supposed to be writing 2-1 all this time. No wonder I was probably thinking I'm stupid. Yeah, all that was supposed to be 2-1, not 1-2. And I can't find my eraser thingies now. Great. Anyways, this one should be 2-1, 2-1. That one was right. 2-1. And that one was 2-1. So I did it right there, but for some reason I reversed it over here because that's there. So I normally like the prefixes to actually match, or the suffixes to actually match. So the way you can do that is you can put a negative on that instead of calling it positive. You put a negative on that, and then you can say R21 either cubed and then say this is R21, or you can say negative G M1 M2 over R21 squared times R21 hat. That works as well. So all of those are valid formulas as long as you make the little corrections I did. But you see how this actually gives you sort of a brute force method of finding out the vector component. You're literally just going to find out what R1 is, find out what R2 is, subtract R1 from R2, and then use that to make a unit vector if you want, and then multiply it. All that works, but these are all valid formulas that work. Again, once you correct my 2-1 versus 1-2 mistake that I made there. Does everybody sort of get that?
I think so.
I put the negative on there because, like I said, I do like them all matching, but it's just as easy to remember them being the opposite of matching. So whichever one you like is fine. And you probably won't use it this semester very much, if at all. But you'll definitely use it next semester when we talk about Coulomb's law. So you guys are free to go regarding that. I think, oh yeah, I did send out an email this morning about that data sheet, the error propagation for those of you who have lab Fridays. So make sure you check your email. I made some changes to that and I got to fix something. So you folks are free to go. I'll wait for the last one to leave so y'all can ask me any questions you might have.
Thank you, Professor.
Thank you for coming.
I have one question about the homework, if you don't mind.
Yeah, no problem. You need to share screen?
Yeah, can I share my screen?
Yeah, it should be available now.
Okay, it's right here, part B.
Okay, let me read the opening. A 3 kilogram box that's on top of a 5 kilogram block, which is on a horizontal surface. The 5 kilogram block is pulled to the right with a force F as shown in the figure. Okay, the coefficient of static friction between all surfaces is 0.61 and the kinetic coefficient is 0.39. Okay, express your answer to 2 sig figs. What is the minimum force F needed to move the blocks? Okay, you got that. In part 2, if the force is 10% greater than your answer for what for A, what is the acceleration for each block? So you're going to say that's basically 92.4 newtons. That should be the force you use. And then since it's actually greater than that, you're going to actually apply the kinetic friction as opposed to the static friction. So with that one, you'll have basically, let me, I think I got all the numbers, 5 kilograms, 3 kilograms, 5.0 kilograms, 0.61, I think was mu static. Is that correct? And
It was
0.
just 0.6.
Oh,
I
0.6.
think it's different for different people. So for
Okay.
mine, it was
Okay, and I'm gonna say 6.1 and 3.9, then I guess that's good enough. And you found your force was 84 newtons. So I said 1.10 times 84 would be adding 8.4 to that. If I add 8 to 84, I get 92. And then I add 0.4 to that, so that'd be 92.4 newtons. So in this case, what we have is a block like that and another block on top of it. So the top one has a free body diagram of 3 kilograms having a force acting on it that is the tension this way, having a normal force that is 3.0 kilograms times G, and then having a force of gravity 3.0 kilograms times G. And that should be it, but it should accelerate this way at the same rate as the other one. Then the other block has a 5.0 kilogram mass. It has acting on it a 5.0 kilograms times G. It has acting on it a 3.0 kilograms times G. That's from the normal force that was provided before. And it has acting on it a normal force of 8.0 kilograms times G. And I assume the force was pulling. So this is the F equals 92.4 newtons this way. And then it has a tension T back that way. Okay. So first off, I have, does that make sense to you, those free body diagrams and everything?
Can
forgot
you
friction.
pull the
Yeah.
paper a little closer?
Yes. And I forgot the friction forces on both of them, by the way. I'm getting ready to add those.
Okay, I think I got that.
Okay. So now I also have a friction force right here, trying to keep it from moving. And then this one, of course, has a friction force acting this way from the block up top, which I'm going to call that F1, but it also has a friction force acting that way, which I'm going to call F2. So it's a lot of different forces on that one. So the first one, I'm going to do T minus F1 is equal to 3.0 kilograms times A, and T minus F1, but F1 is mu static times F normal, which is 3.0 kilograms times 9.80 meters per second. And that's equal to 3.0 kilograms times 9.80 meters per second. So that's my free body, or that's my F equals MA for the 3 kilogram block. And we're saying that's 0.39. And, oh, I said 9.8. That's not 9.8. They're asking for the
I was
acceleration.
about to say that.
Thank you. Yeah, that's supposed to be A, the acceleration. I got mixed up with my G's there for a second. So that's supposed to be A, the acceleration. So I've got T minus, let's do that math real quick just to get that out of the way. So 0.39 times 3 times 9.8. So that's T minus 11.46 newtons is equal to 3.0 times A. I'm just going to leave the units off now. I'll get rid of those tensions earlier, or that Newton later. So that's going to be equation 1. Now the other one's a little bit more crazy in that I have 92 newtons is going in the positive direction, which is the same way I considered T to be pointing. So 92.4 newtons. Now I have minus F1, which we decided was 11.466 newtons. And then I have minus F2, which is 0.39 times 5.0, excuse me, times 8.0 kilograms times 9.80 meters per second. So that's the F2 there. And that should be all the horizontal forces acting. And that's got to equal 5.0 times the same A that we got in the other one. So let me do that math. 0.39 times 8 times 9.8. So I got 92.4 newtons minus 11.466 newtons minus 30.576 newtons is equal to 5.0 times A. This will be equation 2. Luckily, this side's doable, so I can work that out. So I'm going to do 92.4. Well, let me double check my math on that too anyways. 84 times 1.1. Yep, 92.4 minus 11.466 minus 30.576. That gives me 50.358. Excuse me, 50.358 newtons is equal to 5.0 times A. So that suggests A is actually going to be equal to 50.358 358 divided by 5. I got 10.07.
Do you need to factor in tension in equation 2?
Oh, thank you. Yeah, the tension was in there too. I wrote it up here, but yeah, there it is. I just didn't put it in. Thank you for that. Yeah, cool. Okay,
Yeah,
so
no
that
problem.
makes more sense. So it's T minus that should all equal 50A. So scratch that. Thank you. That's a good catch. 2. Thank you. That should be T minus that. All right, now I got a system of 2 equations, 2 unknowns. Luckily, actually, this should be 50. Oh, minus T. Sorry about that.
Yeah, negative T plus.
Yeah, negative T on this one because
Okay.
everything is that way, right? So now we
Yeah.
can add 1 and 2 and the T's will cancel out. So 1 plus 2 gives me the T's canceling out and I will get 50.358 newtons minus F1, which we found was 11.46. is equal to 8.0A because 3 and 5 is going to add. So just adding those 2 equations gave me this. And now I'll do 50.38. Actually, I'll steal it. So I'll do 50.38 minus 11.46. And that gives me 38.892. Newtons is equal to 8.0 times A. So A should be 38.892 divided by 8. And that gives me 4.86 meters per second every second. And I didn't keep any track of sig figs on that. I just ran with it. So that's how you should go about solving it. I hope that makes some sense to you. Like I said, I didn't pay any attention to sig figs. I was just trying to give you an idea of how you go about doing it. You've got to remember that Newton's third law is at play here. So if there's a normal force on the 3 kilogram mass, then that normal force has to be supplied from something, and that happens to be coming from the 5 kilogram mass. So that means that's going to be acting downward by Newton's third law on the 5 kilogram mass. Does that make sense?
Yes, sir. That makes sense. Thank you.
No problem. Hopefully that helps.
Oh, it did. Thank you.
No problem. Anybody else have anything?
Yes.
Yes, go for it, Tristan. This is about lab. Did you need a private moment? Because I can make a breakout room. We can do that right quick.
It's not a big deal. I just have a question about the actual lab itself.
Okay, go for it.
My the lab, I finished all of it except for the graph that we have to. Do we have to draw it by hand?
There's one that's supposed to be done by hand.
Is there a specific graph you want us to graph?
No, you can do either one. Really, I don't care, but I would like you to just do one and try to fill up as much of the paper as possible. You might have to
Okay.
switch to landscape mode instead of portrait mode or something like that. But I just want
Okay.
you to work out once through the details of finding the biggest X and the smallest X and the biggest Y and the smallest Y and trying to make that fit in the appropriate number of squares.
Okay.
Use regular graph
So-
paper, or you can use the graph paper they gave you.
And what about the Excels we build, the graphs?
Everything they ask you to graph, one of those should be made into a hand graph, but everything, including that one, should be made into an Excel graph. And when they ask you to make it, make sure you post it in that part of the lab write-up.
Okay, so you want us to put the Excel graphs into the graph itself too?
Yes,
Okay, I still got that.
into
I still got-
the document.
If I can
I
add
haven't
something,
dropped it.
Go ahead, Christian.
you can copy the Excel graph and paste it into Word. So the physical graph itself in Excel, and you also can import Excel sheets into the Word document too.
Oh yeah, that is kind of nice to do it that way. So you don't have to do screenshots and all that.
Yeah,
Yeah, there's multiple ways you can snip, screenshot, or copy paste. Yeah.
Yeah, I use my
Cool.
snipping tool a lot.
but I just want to know, you want us to graph, on the hand drawn one, what do you want? What material you want into? You want the dots, you want the slope, you want the
Yeah, so you're
Understood.
supposed to lay the dots in the appropriate places and then write the coordinates of them nearby so I can verify that you put them in the right place. And then
Okay.
you're going to try to pick a line of best fit, and then of course figure out what that line of best fit is by doing actual data points. You don't want to measure blocks and just divide, rising blocks over running blocks. You want to actually take 2 data points on the line you made and do rise over run and calculate the slope and the intercept that way. Just to
Okay.
see how well you can get to what Excel chose.
Okay. Oh, also I need the Q1 and Q2 for the extra credit and Bohr's radius.
Oh, okay, Q1 and Q2 is 1.602.
1.6, what?
Q1 equals Q2 equals 1.602 times 10 to the negative 19th coulombs. So that's the charge of the electron and the proton. The electron, of course, is negative and the proton's positive.
And you
And
said
then the
negative
Bohr-
19.
Yeah, negative 19. And the Bohr radius is 5.42 times 10 to the negative 11 meters. You'll probably find out whether or not you need that. That's something to think about. And if you are using an ebook, like with the mastering, you can do a search for those terms, and that's like the quickest way to find these constants when you're looking for them. I'm old school, so I like open a book and look over pages, and I'm like, God, man, electronic book would be so much easier.
All right, so Q1 and Q2 are the same.
Yeah,
So we're just going to be squaring them and then dividing it by the radius squared.
yeah, and then times the K.
Yep,
Remember the
times
K
K.
was the K for Coulomb's law was
8 point.
yeah, times 10 to the 9th.
Yep.
8.99 billion.
Thank you.
No problem. Anybody else?
Also with the labs, both 4 and 5 are due a week from now, right? Because of the confusion.
Yeah.
All right, cool. Just wanted to make sure before because what I want to do is like try to get the lab 4 before like I turn in lab 5 because I want to make sure of some things.
Gotcha. Yeah, and when I screw up like this, I'm really work hard to make sure I make up for it to y'all. So now's the perfect time for someone to turn in something late and get full credit for it. So
Okay. Yeah, it's fine. I was just making sure before.
Which labs are you talking about, David? Are you talking about the labs that we just did with the graphs? Or are you talking about the ones with the velocity?
The ones where we're using Excel. So the one
Okay.
where you're talking about
Okay,
that
the
we
one I
just
was talking
did
about
this past
too.
week. Yeah, and
Thank you.
yeah, we jumped 3 to 5 and skipped 4.
Yeah.
So.
yeah, so I made them both do a week next week.
It honestly wasn't that bad. It like
No, the
that-
Excel was
it-
great, actually. It was very easy.
Yeah, no, it's
Yeah.
not terrible, but
For most, a lot of engineering and math majors, they know Excel already, so you could probably skip that, but I really shouldn't have. It was bad of me. So, but I appreciate y'all being kind.
Yes, sir.
Yeah, I saw the email. I was like, "What?" And then yeah, it all worked out.
Yeah.
Well, I usually get it done by a week. I try and get the lab done by a weekly.
Yeah. That's cool. Well, holler if y'all need anything. I can set up a Zoom session if y'all get confused because it's been so long or anything. Just let me know.
Thank you, sir.
all right,
Have a
sounds
good
good.
weekend.
Thank you.
See ya.
Hey,
Have a good one.
Professor, I still got a question for you.
No problem.
Well, it's more of a statement than a question. I'm going to be heading out of town on a Thursday.
Mhm.
I'm going to a funeral. My uncle died of
I'm sorry.
COVID, so I'm not going to be. Of course, I'm not going to be at class
Right.
Thursday, and then I'm going to be out of town Monday. And well, I'll be getting back in town Monday night. I don't know about my availability on Tuesday.